now, PC Wiz, who has worked with audio networks, will tell us a little bit about how you can get your time should the network time protocol not be precise enough. Please have a round of applause for PC Wiz.
Well, I'd like to thank the content team for rescheduling my talk. And now it really is about time for me to present it. Okay, let's see if you're all actually awake still. Can someone tell me what time it is? 3 p.m.? Bit more precise than that? 3:01. You've got seconds, milliseconds maybe? Ah, fantastic. Show me on the screen. See, we never really know what time it is, because if I ask you what time it is, there's a bit of a delay. Oh, interesting, my slide deck is... Oh, it is working, fantastic. Obviously, a diagram for a bigger stage than this. But just using this example, we're in a room and we're using sound to communicate. Therefore, we are limited by the transmission of sound, about 340 meters per second. So if you're standing 25 meters away from me, it's at least 72.9, 73 milliseconds before you've even heard what I've said. Then you've got to process that, then you've got to send it back to me, and my time is already out of date. And that's really a fundamental problem with knowing what time it is. Because the time I think it is different from the time you think it is. And for a lot of applications, we need to have a better idea about that. There are a lot of things in life where knowing it's 3 p.m. is okay, knowing it's 3:01 is okay, knowing it's 3:01 and 35 seconds is okay. But perhaps we need to know it more precisely than that. I'll get onto those in a moment. But then there's the other thing. We need to know what the rate of time is. Time has a frequency. It's generally 1 second per second. Yeah, right? We like seconds. But let's see how awake you all are. Let's see how synchronized your clocks are. So what you're going to do is count to 10 with your eyes closed, and when you finish counting to 10, put your arm up, and we'll see how synchronized you all are. Okay? Okay. Well, try to count 10 seconds in your head, and then put your arm up after you've counted 10 seconds. Okay, we'll start in 1, 2, 3. Surprisingly well synchronized. But you're not just synchronized, you're syntonized, right? So this is two similar different words. There's synchronization at a moment in time, at an instant in time. I know what time it is, and then there's also syntonization. I'm counting time at the same frequency. And you can imagine why that might be important if you ask for time, and when you want to keep track of the time by yourself until you can next ask for the time again. Or you want to perform a movement in synchronization with something else. Very essential to modern life. So applications of precise time, and I'm talking about precise time here. I'm not talking about network time protocol. Your fuddy-duddy gives you a time within tens of milliseconds, potentially milliseconds if you've got a really good sync. Because with network time protocol, anybody who has tried to read logs from multiple systems will probably know that the moment you start comparing logs from multiple systems, the order gets a bit mushy, right? It's not too bad. Generally, you can see what's going on. But, you know, this imprecise time is good enough for that purpose, but it's not good enough if you have a giant robot arm which will collide with the other robot arm, if it's not very precisely timed, if the movements aren't precisely interlocked. And then, of course, for scientific purposes, if I want to take a bunch of measurements at different locations, and I would like to take those measurements all at exactly the same time, then I need to know what exactly the same time is, and then record that time. So there's definitely NTP would not be good enough for that, depending on what type of science you're doing. And then there's audio and video. For example, not in this stage, but if you go to stage A, I believe there's a line array system. If you are out of sync by about 5 nanoseconds there between the different boxes in that line array system, then you will start to get phasing and interference, and it will not sound very good. Basically, the principle with which that line array operates will not function anymore properly. So you need precise timing in order for like everyday technology to work in that fashion. Financial trading, obviously, knowing the list of transactions, when they happened, what order they happened in, generally a good thing. Right. Okay, let's start with the PTP basics already. I apologize for the terminology, but it's the terminology used in the standard. Complaint to IEEE. So we have, in the basics, we have a master, a lead clock, and a slave clock who wants to know what time it is. So our master clock you can think about as just it's the clock in the room, and it's an old-fashioned clock. It basically tells you the time without you even asking for it. You can hear it click. And that click is a sync message. And what the master does is it records the time of its sync message. But it doesn't send you the time it recorded in the sync message, because unless you have very special hardware support, it just wants to send the message and measure at the last point when that message came out of the master, that was the time. Then it knows the time. And then, but it can't add that to the sync message itself, because then it would interfere with the measurement of the time. So, you know, a bit of interference can't happen. And then the slave, well, it has a clock already. It's probably not a synced clock, but it's going to use it anyway, because that's the best it's got. And then it's going to take this timestamp 2. So it's going to take the time at which this sync message arrives at it. It's going to take that time as precisely as it can with its own clock. So then it knows timestamp 2. And then there's going to be a follow-up message, which the slave doesn't need to ask for, the master just sends it. And that follow-up message contains timestamp 1. So now the slave knows the time that the master thought it was when it sent the sync message, and it knows the time that it thought it was when it received the sync message. It's already a good start. So we just need to do 2 more things. Now we're going to send a delay request to the master from the slave. So it does basically the sync message in reverse. It says, what time is it now according to my clock, which it hasn't adjusted yet. And it stores that as T3 when this delay request goes out. And then the master goes, OK, I've received this message. I'm going to take a timestamp and call that T4 and send it back. So what we're left with are 4 timestamps known by the slave, which are going to enable us to calculate basically 2 things. We want to know what the distance between the master and the slave is, because it takes time for the message to travel across the network. And then once we know the distance between the master and the slave, we want to know what the offset of our clock is, how out of sync our clock is, which is different to the distance. But to know the offset, we have to know the distance. Yeah, and to do that, we have some maths, very simple maths. You take the first 2 timestamps, you diff them. You take the last 2 timestamps, you diff them. You add them together, you divide them by 2, and then you've got your path delay. It's pretty straightforward. And once you've got your path delay, you can use the first two timestamps again with your path delay, and then you get your offset, which is then how much I need to adjust my clock to be synchronized. And then there's another aspect of this where we want to synchronize our clock, so we maybe can adjust the frequency of our oscillator, and we want to know in which direction to adjust the frequency of our oscillator. So what we have to do then is we have to do basically 2 or more of these syncs, and basically compare the time of those 2 events, and then that gives us a correction factor. Oh, good. I'm filling more time than I thought it would be. That's always good. Almost thought I wouldn't have enough slides. So just as a table to run through the calculation a little bit for the synchronization. So you can have a positive offset or a negative offset, or you can be perfectly in sync. It's pretty straightforward. And also to point out that T2 and T3 are timestamps coming from this slave clock. So you're actually using unsynchronized timestamps to come up with a synchronized time, which is kind of clever. Okay, so it's not very useful to synchronize time when you just have one thing. If you just had one master and one slave, it would not be very interesting. You could just build a very precise clock into one device and be done with it. You have to do this to multiple devices. We want one master and multiple slaves. So to do this, PTP uses, well, in this context, to do this, PTP uses multicast networking, so IP multicast. You can run PTP over many different things, but one of the things you can do is IPv4 multicast. And for the network nerds among you, this is a inter-domain control multicast address, which means you can route PTP between networks if you really want to. And these are the port numbers. And basically, by default, all of the messages go to this multicast group. So everybody participating in the in PTP will receive all of the messages. So you can also snoop on your peers and find out what else is syncing, what else is going on. But there's an option, particularly for the delay request messages. These are like a request response thing. So these work better over unicast. Most implementations support doing this over unicast, so you don't spam your entire network with requests and responses to clocks that you're not interested in. What else we got here? Right. So we've got multiple devices in our network, and we need to decide which one is actually going to lead us. Who has the best idea of the time? And PTP tries to solve this problem too. The way it solves this problem is it's interesting. But basically, what you do is you send an announcement message into this, say, multicast group, and you say, my clock is awesome. My clock is more awesome than your clock. And there's like a priority field, there's 2 priority fields, and you basically say, okay, my clock is backed by a satellite, my clock is backed by an atomic clock, my stability is like this, and you can give all kinds of parameters, and basically every clock then decides by itself, according to its own policies, what clock is the master. So you can end up with multiple masters in a network from different perspectives in the network, which is actually something which is used. You basically have full autonomy of each clock. It's not locked in unless you have an implementation which does that, but it's out of scope. But all you really need to know about the best master clock algorithm is that basically each clock decides, am I going to follow this clock? Am I actually the best clock in the network? Therefore, should I become the leader? Which is also an option. These are the decisions that every clock in the network makes. Okay, yeah. And now we have to decide briefly about timescales. So there are 2 timescales in PTP. You can either do the standard PTP timescale, which is TAI second, so the second that we all know and love and appreciate. And there is ARB, which is arbitrary, like completely arbitrary. So if you have a use case where you really want to synchronize something and the second just isn't the best unit of time for you, then I don't know, maybe we can try and synchronize in inches, or we'll find something to we'll find some other unit of time measurement. You can do that. Synchronizing winker cats, so that's also a good idea. Yes. And of course, why wouldn't you have more than one type of time on your network at any one time? PTP uses what it calls domains, which are like an administrative grouping of clocks that all function together as one as one PTP domain. Domain is basically the best word for this. So you can run multiple clocks, multiple frequencies on the same network. And it's basically just a field at the top, and it says I'm domain 0, which is the default domain, or it says I'm domain 1 or domain 2. And you can use domains to do different things. So you could have a clock which is in your standard PTP timescale, and you could have a clock which is in your arbitrary timescale, or you could have different profiles, which are also a thing. So for different applications of time, you have different requirements for how synchronized you are. So that will tell you things like how many syncs should I do, how frequently should I send sync messages, and things like this. So you can also configure different properties to tune the precision of the time you want and operate multiple of those at the same time, or simultaneously. Yeah. So of course, at a certain point, your network gets very big, and you have a lot of clocks that you want to synchronize, and the Grandmaster can't take it anymore, because the Grandmaster has to answer all of these requests and responses. And at this point, we need boundary clocks. There are other reasons to have boundary clocks, but one of the reasons is to scale up your network. And what a boundary clock is it is a slave clock and a master clock. So it synchronizes from the upstream master clock, keeps its internal clock as synchronized as it can, and then basically intercepts and answers all of those request response messages. Well, it doesn't intercept them, it acts as the master. So this S1, S2, etc., they basically treat this boundary clock as the master, while this boundary clock is treating the grand master, which is the bestest clock. As you know, you can have many levels of this. It can get quite interesting. The other reason to have boundary clocks is when you're like crossing subnets, and then you can have like a boundary clock where the slave port is in one VLAN and then the masters are in the other VLANs. So you can do all kinds of fun network topologies with this. The other fun type of clock, because it breaks a lot of things, as I'll talk about later, is the transparent clock. And the transparent clock is, well, transparent. The slave doesn't really know that it's there, apart from there's a magical correction value now added to the packet as it goes through. So this path delay calculation, it works really well for like a piece of cable, because the time it takes for a message to travel along the piece of cable is pretty much determined by how long the cable is and what type of cable it is. But the moment you have a network switch or a router or something in between, then you get variable amounts of jitter in that path delay. So you want to compensate for this uncertainty in your measurement. So the way to do that is you tell all of the networking hardware in your network, hey, be a transparent clock. So what it does is it receives the packet coming in, takes a timestamp, receives a packet coming out, takes a timestamp, calculates the amount of jitter it introduced into that packet, adds it to the packet, and shoves it out the door. So it tries to compensate for the fact that your switch has a buffer in it. It tries to sort of, this is one of the fancy tricks to getting high levels of synchronization without having literal cables everywhere. Right. Next slide, please. Okay. Well, we're at a hacker conference, so let's talk about securing time. Securing time is possibly a bit of a interesting topic, because if you haven't picked up already, the precise time protocol works mostly on metadata about the messages and not necessarily what's in the messages. So we're not what's in the messages doesn't matter so much. It's how long it takes the message to get from one place to the other, which is the thing we're kind of measuring mostly. But it doesn't stop them inventing something. So the latest thing in PTP is the authentication TLV. TLV is type length value, which is a magical bit of metadata which you can attach to your PTP messages. There are different TLVs, but we'll talk about the authentication TLV. And this authentication TLV is supposed to be used for checksums, effectively, for signatures of the messages. So you're supposed to be able to authenticate a PTP message. And because it's an IEEE standard, it's wonderfully complicated. So we have lots of different things you could put in this option. You can disclose a key. Very interesting. We'll talk about it in a minute. You have a sequence number, which seems relatively reasonable. You have a reserved section of arbitrary length, because why wouldn't you? And then eventually you have the actual ICV, the actual checksum at the end, which again is arbitrary length, but you should decide on which checksum you're going to use. The standard says the minimum is a HMAC SHA 256 128, so it's not too bad. The checksum part is okay. And then you have this sec parameter indicator, which basically tells you which one of these fields is going to be present, or all of them, including the reserved section. So DP for disclosed key, SP for sequence number, and then RP for reserved. So why not? And you also have a key ID, which is useful for signatures generally, what you would expect to be there. Okay, I think the next slide is interesting. Right, yes, so immediate auth, because why wouldn't you have two different types of auth in your standard? So immediate auth is intended to be something that you can do pretty much on the fly, very cheap. You can say this message is valid, it came from someone I trust. It's a very simple system, basically. It's based on RFC 6407, and basically you distribute a shared secret with a key server, and you use this shared secret among all of your participating PTP instances. All of the messages should be signed with a shared secret, so it's all right. At least that the message came from a participating PTP instance. At least that most of the message came from a participating PTP instance, because if you remember transparent clocks, they add this magic correction field onto the packet, and this is never covered by the checksum. The standard just goes, so if you want to edit the clock, just edit the correction field. Anyway, so immediate auth. I lost track slightly. As I say, you have a shared secret among all participants of the network. So any any compromise of any one node, and you can say I'm the master now. You can say what time it is. You can answer requests. You can do everything as anybody else. So any clock can impersonate any other clock. But it's better than nothing, right? Well, it's all right. Now we have the slightly more fun auth, which which is asymmetric cryptography, but not the asymmetric cryptography you're thinking of. You remember this disclose key field? This is asymmetric cryptography with time, not asymmetric key pairs. So what you basically do is using an RFC from 2005, this Tesla, as it's called. You use a key, and then the reason it's called delayed auth is that you use a key for, say, a day, and then you reveal the key after a day, and then you're not signing things with this key anymore, so that you can store up all of the messages and verify the signatures a day later. So this is delayed auth, right? So you know, it's so the password for today is Tuesday, and you know, on Wednesday I can tell you the password for Tuesday, and you can see that all of the messages were fine, which is interesting. The other interesting thing about this is, of course, it requires a rough time synchronization to even work. So you kind of need to know what day it is for which key I'm supposed to be verifying the message for. So it's very interesting, and it has the same problem with transparent clocks and correction fields. There are bits of a message which just aren't signed. Aren't signed. The standard says, I don't know what to do about this, so we're just not going to address it. Do something. But at least there's a really good way to derive the keys specified in the standard. What you do, according to the standard, is you pick a random number, and then you decide how long you would like to use this random number as the root of trust for your PTP. And once you've picked this random number, say 365, we'll have 365 days, you just sort of hash it that many times, and every day you just hash it one day fewer times. So you start with, you know, my random number hashed 365 times, and then you get my random number hashed 364 times. And it's beautiful. And then you can validate the entire chain for an entire year. It's a solution. It's a cryptographic solution to possibly something that you can't solve easily with cryptography. Yeah, delayed auth. It's fantastic. If you want some fun, look into Tesla. Where were we? Yeah. Okay. So I should now say that the authentication TLV is from the 2019 version of the PTP standard, and I've never seen it in the wild. So maybe somebody uses it, maybe somebody doesn't use it. But what people actually do is either MACsec or IPsec or one of the two. I mean, this has problems when you're trying to establish precise time, because you're adding an extra layer, you're adding extra delay, you're adding extra opportunity for jitter. With MACsec, it's not so bad, because your switch could, in theory, also participate in MACsec, and you would have authenticated packets between the switch and the clock. But with IPsec, obviously, the moment you start encrypting the packet, the moment you start signing that packet, the switch can't really participate in that. So you lose the ability to have a transparent clock in your switch. You might be able to have a boundary clock in your switch, but it's you know, you lose some accuracy, you lose some precision. Might be acceptable in some use cases. It is acceptable, but in most it's not. So what are the actual practical solutions? Because I don't think the standards actually help. So most PTP implementations let you define a list of accepted master clocks. So do that. That helps. You can also basically tell clocks to either be a master the whole time or be a slave the whole time. You can configure your clocks to only do what you expect them to do, and then they won't surprise you. I mean, the other solution is ignore it, maybe. Where were we? Okay, yeah. So I mentioned multiple domains earlier. There are interesting solutions where you put every clock effectively in 3 PTP domains and then decide whether your PTP domains all agree with each other. The threat model of this is slightly interesting because I would assume you're running it over the same infrastructure, so does it really help you? But for physical redundancy, maybe, if someone unplugs a cable, then having multiple PTP domains could help you. If you run them over separate physical infrastructure, but if you run them over the same infrastructure, then it's very much point. So this is also this inter-domain interactions thing. You can compare multiple domains. A bunch of features you can disable. For example, I showed an example of a two-step synchronization. If you're only doing two-step synchronization, you don't need to do one-step synchronization, which is the same thing, apart from that you do actually get T1 in the sync message because the master adds it magically at the end with hardware. And the only thing that really works, to be honest, is monitoring your clocks. Oh yeah, I missed a thing. Back to Tesla. So I've still got time, and I've missed what I wanted to explain here, which is really the interesting bit. So because this is time-based, and because you control the correction factor, you can effectively desync a clock to the point that your man in the middle has the the slave clock is trusting a key, right? And the key is not being disclosed yet. But you can make this slave clock enough behind that you can get then this disclosed key and keep the clock behind, and now you control this slave clock. Although it doesn't really win you anything because you already desynced the clock, which is why I was talking about monitoring, because you're going to notice that your clock is desynced. So I think the thing to learn from this is that trying to sign these messages just isn't very helpful, and you should just check what time it is at various different points in your network, and your application will probably break, but don't rely on your application breaking. Yes. I think the other thing that people suggest is just having more stable clocks. So if you just want to build like a GPS into everything and have every device in your network have a perfect view of the sky, then you can have relatively reliable clocks as long as you're not in a war zone. I think that was it. Yeah. Okay. Well, that was quicker. I guess we have Q&A time.
Thank you, PC-Wiz, for this interesting talk. We have actually quite some time for Q&A, so there's a mic. If you have a question, just go over there.
No? Use that mic.
Oh, okay. So if you have a question, just raise your hand and we'll come with you to you with a mic over there.
actually on? Yeah, okay, now it works. So how does PTP deal with drifting clock frequencies? So I can imagine if you need really precise, then your system warming up is going to matter.
Like the drifting clock frequency, so you have, according to your PTP profile, you set the rate of synchronization messages you send, basically. So you can decide how often you want to check in. Okay. And to like drift, for the drifting clock frequencies, we go back to here, right? So this correction factor is what you have to calculate, and depending on what you're running on, you can try to adjust your internal oscillator with that correction factor.
So you do this over and over?
You do this over and over again, but you basically do this continuously. Okay. And the profile defines some things about that.
In the front.
I would have maybe like new question. So how far you can get with PTP? Like what kind of network can be between the clocks for it to still works reliable? Like is it only layer 2 network, or can it be also router? Can it be over the internet?
I mean, you could do PTP over the internet. I wouldn't recommend it. I know people who do PTP across continents, but it really depends on your use case. So, like, the level of synchronization you can get with PTP is, for most people, nanosecond level synchronization. For some people, picosecond level synchronization. I believe CERN have a add-on to PTP called White Rabbit, which does really crazy things. There's a bunch of, so it's not reliant on being on a local layer 2 network. The protocol is fairly agnostic in that regard, but there is a bunch of stuff in there about correcting for link asymmetries and different media types, and as I mentioned, but perhaps fumbled a little bit, you don't have to run PTP over UDP in an IPv4 environment. It runs over lots of other different types of layer 2s and layer 3s if you really want to.
Is there also support for IPv6?
Of course. Yeah.
Thank you.
What exactly does PTP, what makes PTP so much more precise than NTP?
That's a good question. Yeah, I think, off the top of my head, it's a bit more difficult to answer. But you have this the hardware timestamping is useful, but because you have you have more frequent synchronization, you have more knowledge about. I'd have to get the NTP.
Is it mostly about the environment that's usually used then? Because NTP is, of course, usually used to just synchronize like once a day to a server somewhere on,
exactly.
on the continent.
I'd have to get the sequence diagram up here because I think there's... Yeah.
Further questions? Yeah.
Yeah, I'll find something.
So with delay authentication, you get your confirmation afterwards that you had been hacked. That doesn't sound fabulous. But if you were to do the delay the other way around, like you would first send a dedicated packet with all the cryptography and all the shit, and inside that you give a token that's valid for the next 10 seconds. Then you could easily have a very reliable source of a very efficient authentication.
What are you going to do with this token?
That token is being used to prove that all those other packets are valid with a very lightweight cryptography algorithm on it. But it's much better than the, how did you call the other one? The shared secret algorithm. So that's, that's a suggestion.
Yeah. Okay. So like you issue the shared secret just on a more frequent interval is basically what you're saying.
Exactly, because if you do it, make it valid for 10 seconds, doing the cryptography, the public key cryptography would be something you can validate in half a second or so, or 1 second. But that's plenty of time for then enjoy it for 10 seconds. And of course you have overlapping keys, so that would be something you could use. But I don't see it as one of the offered options.
Yeah. I mean, if you want to propose that the IEEE next time they revise the standard.
Okay, maybe. And I have a very short second question. I missed the first 5 minutes.
Yep.
There is, I believe, an RFC 15 or IEEE 1588 or something.
Yes.
Is that the same thing?
Yeah. PTP is IEEE 1588. PTP version 2 is -2008, and there's the latest version 2.1 from 2019. And in 2019, this authentication option is added.
Okay, so this is RFC, the IEEE 1588.
Yeah.
Okay. Thanks.
Further questions? Yeah, over there.
Hi. I have a use case for the arbitrary time. I was wondering if there is also a way to stop time, resume time, and go back in time.
Back in time, like, might be tricky, but you control the values that you put in the messages, right? So you can say, you can slow down clocks by answering messages with a different T1 or a different T3. Those timestamps you can put in whatever you want. You can make the slave believe whatever you want. It's going to trust you.
Okay, so you basically, if you tell the master what time you want to go back, then
well, yeah. I mean, that's up to you as the implementer of the master what you want to say. Like, it's also up to you as the implementer of a transparent clock what you want to put in the correction value. I mean, you're not going to put like a negative value in there, but you can also put a large positive value in there.
Okay, that's clear. And about stopping time.
Stopping time, I mean, you can turn PTP off. Like, you can stop answering the messages. Like, what's going to happen then is the slaves are just going to continue trying to count time by themselves, and like your application will eventually break. But it really depends.
Okay.
Any further questions? That's not the case, then give another round of applause for PC Wiz.